Hello, I am Astronomy to GCSE and this is an introduction to Feynman diagrams. This was a presentation I gave to my Physics Society about a year ago. I have slightly adapted it as I don't have a whiteboard and I hope you're interested. This isn't part of the normal Astronomy to GCSE videos, it's not part of the syllabus. Don't worry, it's just something extra I thought you might be interested in. Richard Feynman was a theoretical physicist in the 20th century. By that I mean that his work was theoretical, not Feynman himself. He was born in 1918 and died in 1988. He was an American physicist and attended MIT for his undergraduate and then Princeton University for his PhD. He then went on to work at both Caltech and Cornell University, and it was at Caltech that he performed his famous Feynman lectures on physics from 1961 to 1963. However, after his PhD years at Princeton, Feynman worked at the Manhattan Project, developing with beta the beta-Feynman formula for calculating the yield of a fission bomb. Afterwards at Caltech he worked on QED, which is quantum electrodynamics, which is where Feynman diagrams come in. Before we get on to Feynman diagrams, I'm going to give you a little introduction into the standard model of particle physics, and that's what we have here. Okay, so this whole table is called the standard model of particle physics, and it contains a variety of what we call fundamental particles. Now, fundamental particles are particles that cannot get broken down any further, or at least we think they can't get broken down any further. And these are the leptons. Now that might be quite a strange word, you may not have heard of that before, but you've definitely heard of one lepton, and that's the electron. So an electron is just a type of lepton. The neutrinos feature as leptons. Each of the leptons, so here we have the electron, the muon and the tau, each have their neutrino versions. So they're the leptons, here they're coloured in green, and now if we look above we have the quarks. Now some of you will have heard of quarks, and there are a variety of quarks. You have up, down, charm strange, top and bottom. So with the quarks they all follow a similar pattern, but we're going to come to the pattern in a little moment. On the side here we have what are called the gauge bosons. Now if you like, these are the fundamental forces which allow our quarks and leptons to interact. There is a term for both quark and lepton generally as a whole group, and that's called fermion, after the Italian physicist Enrico Fermi. So the gauge bosons contain the gluon, which carries the strong force. Now the strong force is for quarks only, so as you can see there's this little outline which goes around the gluon. Now the gluon is a quark only club, so only quarks can interact with the strong force and therefore interact with gluons. We then have the photon here, and you'll probably have heard of that because it's a particle of light. It also is part of the electromagnetic spectrum. That's what light is. Now the electromagnetic force, so both the electric and the magnetic forces are carried by our photon. Now these are all charged particles, so if you see the line that goes around the photon, it also extends around the electrons, the muons and the taus, and all the quarks. That's because these three rows and columns here are all charged. The neutrinos down the bottom, they're not charged, so they can't interact with the electromagnetic force, and that does come up later, and it is quite important because it means you know when you've got a Feynman diagram, if there's a neutrino involved you cannot have the electromagnetic force. So just as the gluon was quark only, the photon is charge only. Okay, so now we come to the Z and W bosons. These carry the weak force. Now the weak force is for all fermions, so this includes neutrinos. So in fact the only particles which can interact with neutrinos are the Z and W bosons. We then also have the very famous Higgs boson, but that's slightly different to our other four neutrinos. So we're really going to leave that out for the minute. What you may notice is that there's these three numbers by each of our fundamental particles. Now these, the top one is mass, which is measured in electron volts, so that's a slightly different unit. If you like, it's a small joule. Now some of you will notice that a joule is a unit of energy, and actually mass is a type of energy. The equation E equals mc squared links energy, E, to mass. And so mass is just a form of energy, so that's why we measure energy in electron volts. Then we have our charge. This is just like protons and neutrons. They have charge. Well, a neutron doesn't, it's neutral, but the charge here we can see for the up quark is plus 2/3, and for the down quark here it's minus 1/3. Now spin is something slightly different. We're not actually going to get onto that in this video. So what we're really going to be looking at is the charge and the mass. Now if you look, the up has a charge of plus 2/3, the down has a charge of negative 1/3, the electron has a charge of negative 1, and neutrinos, as mentioned earlier, are chargeless. Now if we look at the next row, column, we will see that the charge is the same as the one across. So this is 2/3, this is all negative 1/3, this is negative 1, and then again our neutrino is chargeless. And again the next column, the same pattern occurs. The up, the charm, and the top all have a charge of plus 2/3. The down, the strange in the bottom, all have a charge of negative 1/3. And then our electron, muon, and tau all have a charge of negative 1, with our neutrinos all being chargeless. So what's the difference between our first column, our second column, and our third column? Well, our first column, as you can see, it's got our energies in here, and we can see that the second column is actually quite a lot heavier. It's got a lot, the mass is much greater. So that's the difference between our first column, which is called our first generation of matter, and our second generation of matter. It's just that the second generation is heavier. And then the pattern happens again. The third generation of matter is even heavier than the second. The bosons aren't their own generation. They're just allowing these fermions to interact. Okay, so if we look at all of the matter that we see in everyday life, that's made of atoms, which are made of protons, neutrons, and electrons. And protons are actually made from the up and the down. Protons and neutrons are actually made from the up and the down quark. In fact, a proton is 2 ups and a down, and a neutron is 2 downs and an up. And if you look at the charges, that's why the charge of a neutron is neutral, because the overall charge is nothing, whereas the proton, which is made of 2 ups and a down, you can see if you add the charges together it comes to 1. So everyday matter, that's all made from our first generation. You find the second generation in cosmic rays, the third generation you find in particle accelerators and colliders like CERN. Okay, so back to Feynman diagrams. Feynman diagrams are pictorial representations of the behavior of subatomic particles when they interact. So they're, if you like, pretty pictures that show what's happening when our fermions are interacting with our bosons. Okay, so Feynman diagrams use our fermions, so the quarks, the leptons, and then each of these have their anti-counterparts. So you can have an anti-up, an anti-down, an anti-electron, which is often called a positron, and then you can have anti-electron neutrinos. So Feynman diagrams use quarks, leptons, and their anti-counterparts, and then bosons in order for these two fermions to interact. As previously said, quarks have 6 flavors. Flavor just means type. We've got our 6 ones here. And then quarks combine using the strong force only to make composite particles called hadrons. So a very common type of hadron would be a proton or a neutron. You also get strange ones that you get in cosmic rays like pions. We will look at them later on. But hadrons actually come in 2 groups. They come in baryons, like protons and neutrons, which are made from either 3 quarks or 3 antiquarks, or mesons, which a pion is an example of. A meson is a particle-antiparticle pair. So that might be a down and an anti-up, or a down and an anti-down, or something like that. Okay, and then there'll be three interaction particles that we use today. So we have the photon, the gluon, and then we'll be using the W boson. Now if you look at the charge of the W boson, it's got plus or minus 1. That's because the W boson, there are two types of that. You get a W plus boson, which is a charge of plus 1, and you get a W minus boson, which is a charge of minus 1. So we'll look at deciding which W boson to use later on in our Feynman diagrams. Now if we look, before we get on to actually using the Feynman diagrams, if we look at the quark interactions, we have our gluon here. Now a gluon exchanges a further charge, if you like, called colour charge between our quarks. Now only quarks have colour, and there are three options we can have. Now they can have, I'll just get a pen, you can have red, you can have green, and you can have blue. Now when a gluon goes between a quark, what the gluon will do is it will, I'll just go back to my laser pointer, what our gluon will do is it will go from a quark, let's say it's a red colour, it will change the colour of that quark, and then it will whiz on to another colour, and then that's how it keeps them together. Now in order for a hadron, which is a composite particle, to be stable, it must be colour neutral. So if you like, here the red, the blue and the green come together to make white. Now what we can, so that will be colour neutral. With mesons, which are a particle-antiparticle pair, what you see is that they are anti-red. Now you represent anti as a line above, anti-green and anti-blue, so we can see here that our baryon made of three antiparticles is also colour neutral, because anti-red, anti-green and anti-blue come together to make a colourless hadron. And then if we have a meson, which is a particle-antiparticle pair, I'll just draw one here, what you will see between it is one will be a colour, let's say red, the other one will be another colour, and that'll be anti-red. So you can see that red and anti-red are going to come together to make our colourless particle. So that's how the gluon acts. Okay, so here we have a very simple Feynman vertex. Now Feynman diagrams can sometimes be called Feynman vertices, or in this case we have a Feynman vertex, and that's because this point here, this interaction point, is sometimes called a vertex. So in a Feynman vertex, time moves from left to right. So this dimension represents time, the other dimension represents space. Now you may be wondering, why do we do that? Why do we have space as only a single dimension? And that's basically because particles down at this level don't act like snooker balls. They don't smack into each other and whiz off the other side and that sort of thing. They act quite differently. They act a little bit like a wave, and they act a little bit like a particle, and this is called wave-particle duality. So it's fine that we are only representing space in one dimension. But it is really important to remember that Feynman diagrams do not show the actual movement of a particle. These are really just pictorial representations. They can help you when you get to really high levels with maths, and they can help you compute probabilities of what's going to happen and how likely something is going to be created. And that's really useful for when you're trying to search for a particle like the Higgs boson, because you can, when you need to know what's the probability of these particles occurring. Okay. So if we have a look, this is if you like the most simple Feynman diagram. We have a particle entering the vertex, there's an interaction symbol, so one of our bosons is leaving, and then a particle, maybe different particle, or it's at least at a different energy, or something's happened to it. This particle, new particle let's say, is leaving the vertex. Now if we look, these are both forward facing arrows, they're facing forwards in time, because remember time goes from left to right. So a forward facing arrow like this one represents a particle moving forwards in time. Now a backward facing arrow represents an anti-particle moving forwards in time. So forward facing arrow is a particle, backward facing arrow is an antiparticle. Okay, so one of the most fundamental rules when generating a Feynman vertex is that the diagram can be rotated about our vertex. So our whole diagram can be rotated about this point here to generate slightly different Feynman diagrams. So by generating a multitude of possible interactions, it can be very useful because you can find different ways of our particles interacting. So the arrows have to, here's the one important rule, when you rotate a diagram, the arrows have to continue pointing in the same direction relative to the vertex. So this one here is pointing into the vertex, this one here is pointing away from the vertex. So that's really important. Now, okay, so here is our Feynman vertex from last slide, and what I'm going to do is slowly rotate it around, and then I'm going to display our three possible Feynman vertices we can develop from this one here. Okay, so we're rotating it, and then we can see that we get this one, and now this one, and finally, as we rotate it nearly back to the original position, we get this one. So if I zoom in onto these three vertices, we see that we have we have a boson coming in and creating a particle-antiparticle pair. Notice that this arrow, because it's stayed facing towards the vertex, has now made an antiparticle. So that's why it's really important to maintain your arrows facing in the same direction relative to the vertex, not to time, relative to the vertex, because it will change whether you create particles or antiparticles. So here, as it's continued pointing relative to the vertex, we can see that we have made a particle-antiparticle pair from our interaction, from our boson. Now here, as the arrow is facing backwards, we see that we have an antiparticle entering, and then again we have an antiparticle leaving along with a boson. So here we've got the same as the one before, but this time we've got a particle entering, a particle leaving, and then alongside this particle we have our boson. So what we're going to be doing now is an example of purely leptonic, so between the leptons only, weak interactions. That's both the W and the Z boson, because remember, both of them carry the weak force. Now, we're not actually going to be using the Z boson, we're going to leave that for now, but we are going to be using the W plus and minus bosons. Okay, so an example of purely leptonic weak interaction would be when a neutrino lepton, so one of these, I've said lepton because it's more general, it's not specifically one of them. So when a neutrino lepton decays into a lepton using the weak nuclear force. Now a neutrino can decay into a lepton of the same generation. Now by that I mean, let's say we've got an electron neutrino, it can decay into an electron, but it can't decay into a muon. Likewise with a muon neutrino, it can decay into a muon, but it can't decay into an electron. So what I'm saying is they can't jump generation. Now the way we represent this on a Feynman diagram would be like this, where we have our lepton neutrino entering, then a lepton of the same generation leaving, along with a W plus or minus boson. Now that's dependent upon the charge of the lepton. Now you may have noticed that because they're all the same, they're just heavier because they're in the bigger generations, that the electron, the muon and the tau all have a charge of -1. So you may be saying, how is this dependent on the charge? Well, if we had an anti-lepton neutrino entering, that's also got a charge of 0, but our lepton that's leaving would become an anti-lepton. So let's say we had an anti-electron neutrino entering, we'd get a positron, sometimes called an anti-electron, leaving. Now that would have a charge of +1, because the difference between matter and antimatter is that the charge is reversed. So that's why it depends which boson we've got. But let's say we have our lepton neutrino entering, because that's got a charge of 0, we've got 0 entering. Let's say we have a standard lepton leaving, let's say like an electron, that has a charge of -1. So what's the charge on our boson going to be? Well, charge cannot be created or destroyed, which means if we had 0 to start with and we've got 1 up there, we must have -1. If we've got -1 up here with our electron, we must have a W plus boson leaving. So that's an example of purely leptonic, so leptons only, weak interaction. So here we have the electromagnetic force. Now the electromagnetic force is carried by the photon, which is a particle of light, which is part of the electromagnetic spectrum, and it's sometimes represented as a gamma. Now, remember that the electromagnetic force is only between charged particles. So we've got all of the quarks, and then the electron, the muon, and the tau. So it's all of the fermions, in fact, but just not the neutrinos. So the neutrinos can't interact using the electromagnetic force. In fact, the only force that they can interact with is the weak force. Okay, so what we see here is a charged particle is moving along. Remember, it has to be charged, and now it emits a photon and it carries on. So what's happened here is it's lowered its energy as it's emitted the photon and then carried on. You can see that because our diagram can be rotated, you can equally have a charged particle coming in and absorbing a photon and then carrying on. Equally, a charged antiparticle can move along, emit a photon, and carry on. So remember, it's the same particle, so it's not actually changed which particle it is. So let's say we've got an electron moving along the electron. Well, here we'd have a positron. So we've got our positron moving along. The positron emits a photon, but the positron carries on. It's not changed, unlike what we saw with the weak force. So now we can see here that a charged antiparticle can equally absorb a photon, and because our Feynman vertices can be rotated, a photon can go along and then become a particle-antiparticle pair. Remember, both of these must be charged. Equally, a particle-antiparticle can come together and annihilate to produce a photon, which is why in the alpha experiments at CERN, which sometimes called which is part of the antimatter factory, people aren't allowed in the area when the experiment's running because it's emitting lots of high energy gamma rays, which are a form of radiation. They're very dangerous. So that's why when matter and antimatter come together, they will just produce energy. There are a number of possibilities we can have with weak forces. Both quarks and leptons can interact using it. So as I showed you before, a lepton neutrino can enter, and then a lepton from the same generation can leave using the weak force. Now, if you want to find out more of the possibilities you can have with leptons and the weak force, then draw this diagram down on a bit of paper and begin to rotate it and have a look at what happens. Okay. So the possibilities with quarks are similar to that of a lepton, but they're also slightly different. So our quark can enter our vertex, and our quark from the same generation, I'll just pull up the standard model here. So now a quark from the same generation can leave, so we'll look at that first. So let's say we have an up quark which is coming into our vertex. It can interact using the weak force. And then let's say one from the same generation, a down quark, can leave. Equally, a down quark could enter and then an up quark leave. But there's this other possibility. A quark from diagonally across on the standard model in a neighbouring generation can leave. So let's say we have a down quark entering. We can have one diagonally across, we can have the charm quark leaving. So a down can enter, a charm can leave. Equally, an up can enter, and then a strange could leave. So it has to be diagonally across, it cannot be horizontally across. So a down could not create a strange, it can only create a charm. Okay, so that's a little bit of an introduction to what can happen with quarks. And again, if you draw the Feynman diagram down and rotate it, you can then see a little bit more of what can go on. Now, if we give a little example to find out what the charge of our W boson will be, we can see that if an up quark enters of charge plus 2/3, you can see that there's a charge of plus 2/3 there, and then let's say a down quark leaves, it would have a charge of negative 1/3. So the overall charge has changed from plus 2/3 down to negative 1/3. So the charge has gone down by 1. So if this W boson is leaving out here, then we can see that it's going to have a charge of plus 1. So our overall charge in the vertex has been maintained. But let's say we had our down entering and an up leaving. Because it's going from a down to an up, we'd have to have a W minus boson leaving to maintain our charge. So that's something to bear in mind. You do have to check which W boson is leaving your vertex, because it will have a knock-on effect later as well. So now on to the strong force. The strong force is carried by the gluon, and it's to do with this non-electric charge called colour that only quarks have. So remember that the strong force, the strong interaction which is carried by the gluon, is a quark-only club. So only quarks can interact using the strong force. Now it is quite important to remember that. You may notice that the gluon is represented slightly differently to the others. It's represented as this curly line rather than the wiggly one we had previously. So remember that quarks have a non-electric charge called colour, and instead of being either positive or negative, the possibilities are red, green or blue. Having red, green and blue is an attractive grouping. However, two like colours repel, so really in some aspects this is quite like our electric charge. So we can't have like colours, and we want to have an overall neutral grouping. And remember that the anti-quarks do have their anti-colour, and red and anti-red would come to form again a colourless attractive grouping. So that is because of these rules of colour combinations. So either we have a red, green and a blue quark to make a colourless combination, or anti-red, anti-green, anti-blue, that we are baryons form, which is a type of hadron. Remember, hadron just means composite particle, and a baryon is a hadron with 3 quarks or 3 antiquarks. So that's why you get that, because you will find that your quarks will find an attractive grouping if their colours all cancel out. And again, a meson with a quark antiquark, they've got to be the same colour to again have that attractive grouping of a neutral colour. Okay, so a gluon can be seen as a pathway for the exchange of colour. So we can see that a coloured quark enters the vertex here and emits a gluon, and it leaves with a different colour. So let's say a red quark enters, it emits a gluon, then a blue quark could leave. It is actually really important to remember that these colour things are not actually to do with colour, because the wavelength of colour is massively larger than these particles. It's just a way we use. It's just a name we attribute to this type of charge. So really, don't think it's actually red or green or blue. It's not got any colour at all. But it's just a name we use. Okay. So here we can see that a coloured quark enters the vertex, interacts with our gluon, and leaves again with a different colour. Here, notice the arrow is facing backwards. So you've got an anti-coloured quark, so let's say this is anti-green, enters our vertex, emits a gluon, and leaves with a different anti-colour. So this could be anti-blue. And here we have an anti-coloured quark, so let's say that's anti-red, is entering our vertex, interacts with the gluon, and leaves with a different colour. So that could be anti-green. And equally, here you can see that a gluon materializes into a quark-antiquark pair, where the quark and antiquark would have a different colour and anticolour. And that's because this is just one of these diagrams rotated. That's why these colour rules are as they are. Now here you can see that a particle and an antiparticle are coming together and annihilating to become a gluon. So this is quite so if you get a quark and an antiquark, they can actually annihilate to a gluon. What you'll actually find is that eventually they'll probably form a photon through further interactions, but a quark and an antiquark can annihilate to a gluon. So now we're going to do an example question so you can get to see how Feynman diagrams can be built up a little bit bigger, a little bit more complicated. So this one we're going to do is beta minus decay. That's a type of radioactive decay in the nucleus of some radioactive atoms. Now what happens here is a neutron in the nucleus, which has a quark composition of up, down and a down, decays into a proton, which is a quark composition of an up and a down, and an electron. That's our beta minus particle. We also have given off this anti-electron neutrino. Okay, so if I get my pen out, we can begin drawing this. So the neutron is a composite particle. Now a fancy word for composite particle is a hadron, and the type of hadron a neutron is a baryon. But hadrons are represented using a curly bracket. So what we're going to have here is a neutron. Now the reason it's represented with a curly bracket is it actually contains more than one fundamental particle. So we're going to now draw in the fundamental particles, the up, the down, the down. So that's why we have our curly bracket, to show that our neutron is containing these three fundamental particles. On the other side we have a proton, so we'll draw another curly bracket, and we have our proton. Now proton is made of an up, and a down. Now I'm actually going to draw it like up, down, up. Doesn't matter which way you do it, but I'm going to do it for neatness here, and you'll see why in a minute. Now we have an electron, so that's like that, and we show the charge of the electron there as a minus because it's not a positron, which would be a plus. It's an electron, and that's what our beta minus particle is. So I'm just going to draw slash beta minus because that's all a beta minus particle is. It's just an electron that's emitted through beta minus decay. We now have an anti-electron neutrino as another one of our products, if you like. Now an anti-electron neutrino is represented with the letter nu because it's anti, has a bar on top, and because it's an electron one, you can have a little subscript e. So here we've got our three products. Now you can see this is why I drew the up, the down and the up as I did, because you can now see that this up on the left here is going to become this up on the right down here. So what we can do here is we can draw a straight line between them, because we know it's not going to change between that. So what we've got here is, because we've got a particle, it's forward facing arrow. Likewise with our down, now that's why I drew the order the other way around, just because it's a little bit neater. You don't have to do the lines crossing over or something like that. So actually what's happening is we're having our down quark change to an up quark, and then somehow with that change we're getting this electron and this anti-electron neutrino leaving. So because we know a neutrino is involved, we know that we can't use the photon. That's not going to happen because a neutrino isn't charged. We also can see that there's two leptons involved, so there's definitely no gluon involved, because well, A, that wouldn't change our down to an up. All it would do is change the colour of the down, and B, the leptons cannot interact using the strong force, so we know it's the Z and the W bosons. Now it's not Z because we've actually got charge changing, so you can see that the neutrino doesn't have any charge, but the electron does. And because the Z boson has no charge, we know that it's going to be one of the charged W plus or W minus bosons. So we know it's this one. So we can show our down changing to an up by having our down change to an up, and that dot is our vertex. And because it's a particle, these are all forward facing arrows, facing forwards in time. Now we know a W boson is leaving. We don't know what the charge is yet, so we're just going to leave that. Okay, so we've got our W boson leaving, and then we can see that it turns into two particles, so we know that there's another vertex. Now if you remember from our purely leptonic interaction earlier, that that diagram I was displaying can be rotated. So and what you'll find is when you rotate it, a W boson, when it decays into two leptons, a lepton and a lepton neutrino, one of them is going to be an antiparticle. That's what you'll find when you rotate it. And so in this case you can see that we've got our antiparticle here in the form of the neutrino, and we've got our normal particle here in the form of the electron. And actually this is a totally valid interaction. You'll find it from rotating that vertex we had earlier, and that enables, and because we know that, that enables us to just straight off draw our particle here. So you can see that the from this interaction with the W boson, we're getting an electron and then an anti-electron neutrino, and because it's an antiparticle, the arrow faces backwards in time. Now, what's the charge of our W boson? Because that is quite important, actually. Well, you see, whatever the charge is in this W boson must be the charge, overall charge of these of the two particles that we've got at the end. So the overall charge of this must be the overall charge of these, because charge is conserved over the Feynman diagram. Now, what we see here is the neutrino's got no charge, but the electron has a charge of -1. So because it's got a charge of -1, we know this is a W minus, because the W minus has a minus charge, and over here we have a minus charge. And because there's no other particle leaving to take that charge away, it actually looks like that. And that's the end of that example question. We have another example question here, where we have a pion plus. Now there are a whole variety of pions. You can get a pion plus, you can get a pion 0 with no charge, and you can get a pion minus. Now you might be wondering what on earth a pion is, and it's a type of meson, which is a particle-antiparticle pair. So again, it's a composite particle. But this time, rather than being a baryon, which has either 3 particles or 3 antiparticles, as we had with our proton and neutron, we've got a meson with a particle-antiparticle pair. Now, you won't find these in the real world, but you do find them in cosmic rays. Okay, so this pion plus is going to decay into an anti-muon and a muon neutrino. Okay, so let's have a look at how we would draw a Feynman diagram for this interaction. So again, we've got a composite particle on this side, so we can draw a big curly bracket here. And for the pion, you represent them with the Greek letter pi, and because it's plus charge, you represent it like that. That's just an easy way of writing pion plus. Now we know we've got an up, and we know we've got an anti down, because remember it's a particle-antiparticle pair, and here I've shown that this pion plus is an up and an anti down. Okay, so that's what we've got going in, and what we've got coming out is an anti-muon. So you represent an anti-muon as just a normal muon, which is the Greek letter mu, and rather than being a minus charge as it would be, as we see down here, the muon is a minus charge, just like the electron, but because it's an antiparticle, the charge is reversed, so it's a plus. So that's how we represent an anti-muon. And now here we've got a muon neutrino. So again, we've got a nu for the neutrino, and the type of neutrino it is a muon neutrino, just like that. There's no bar this time because it's a normal neutrino, it's not an anti-neutrino. Now, if you remember, I said when you rotated the purely leptonic weak interaction we had earlier, you'd find that one of them, either the lepton or the neutrino lepton, would be an antiparticle. Well, previously we had it as an electron neutrino and an electron, whereas in this case we have an anti-muon and a normal muon neutrino. Okay, so if we have a look in this interaction, we know that there'll be a vertex, so we'll draw that there. So we've got our up quark coming in. Now the arrow faces forwards because it's a standard particle, and here we have an anti-down, so we can see that the arrow is facing backwards because it's an antiparticle. Okay, so because these two are annihilating, as I showed you earlier, they could annihilate into a gluon, they could annihilate into a photon, and they could annihilate into a W boson. The reason they can't annihilate into a Z is, have a look, that's got this is an overall charge of a plus. Z has a charge of 0, so it can't annihilate into a Z boson. It's got to be a W plus. So actually, it's got to be a W plus, more specifically than just the W. But have a look what we have on the other side. We have a muon. Now that's charged, so it could be a photon, but it's not a quark, so it can't be our gluon. So now we've got it down to a photon or a W boson. But because you can see we've got our muon neutrino there, they're not charged. So that means it cannot be our photon. So what we've got here is we've actually got another weak interaction. So we've got another weak interaction. So we'll draw our W here. And actually we can do the charge quite easily because we know the overall charge of the pion was a plus. So we know again it's a W plus boson because all the charges all the particles have gone into this interaction point. We know the charge must be maintained. And then you can see that our anti-muon with the arrow facing the other way and facing backwards is going to be coming out into the vertex, and then we've got our muon neutrino there. So that's okay. I apologize that we don't have a bracket here. I couldn't manage to make that. Okay, now on to our final example question, where we have an anti-muon changing into a positron, an electron neutrino, and an anti-muon neutrino, which should have a line above it. So what we can see here is we don't have a composite particle, we don't have a hadron entering our vertex. What we instead have is just an anti-muon. So there's no curly bracket. And then on this side we have a positron, just again for neatness I'm going to draw that down there, and then we have our electron neutrino, so the nu for the neutrino and subscript E for the electron, and an anti-muon neutrino, so straight line for the anti, nu for the neutrino, and mu because it's a anti-muon neutrino. So what we can see here is that our muon, our anti-muon, is going to change into our anti-muon neutrino. Now remember our purely leptonic interaction. Again, if you rotated the vertex, you'll be able to see that with the arrows all facing the other way, you can have this interaction. And we know that it must be a weak interaction because it's got the neutrino involved. The neutrino is a really good indicator that a weak interaction has happened because it can't interact with the photon or the gluon. So remember, these are antiparticles, so the arrows face the other way, and we have our boson given off. Now you can actually work out what the charge is, because the charge of the muon is a plus. It goes to a charge of 0 with our anti-muon neutrino. So the charge has all left with the W boson, so we've actually got a W plus here. So this W plus boson becomes these two other particles, our positron and our electron neutrino. And just like before, you can see that again by rotating that purely leptonic weak interaction we had earlier, you can find that we can have a positron and a neutrino emitted. And remember, I said you'd find that one of them, if it's a W boson becoming two leptons, I said that one of them you'd find that one of them would be a antiparticle and one wouldn't. In this case, the antiparticle is the positron and our electron neutrino is the normal particle. So that's what we have here. In fact, we've got no curly brackets because we have no hadrons. Again, another example of the weak interaction. So that's a neat version of what we showed earlier, again with our W plus and our weak interaction. Now I have for my talk I compiled a practice question sheet where I gave them about 9 questions that they could go and do. So I've made this sheet available for you. I've put it onto TES, which is a Times educational supplement. This link will be in the description. So if you want to go and download that sheet and do those extra questions, then by all means do. If you have done that sheet, then here's some more complicated examples. Basically, of where we have a cation plus becoming 2 pion pluses, if you notice, and a pion minus. This is slightly more complicated, and so I will go through it now. Okay, so you can see that the cation plus is a composite particle. It's comprised of an up and an anti-strange. Now on this side we've got two pion pluses, so I'll draw the brackets first. It's going to be quite cramped because we've got a lot coming out. We've got two pion pluses, and then our final one is our pion minus. Now we have an up and an anti-down for our pion plus, and again we have another up and another anti-down, and here for the pion minus we've got a down and an anti-up. So you can see that actually you've got an up and an anti-strange turning into a whole load of particles, and you may be going, surely there's some conservation law that doesn't allow this to happen, but actually it can. This is a perfectly legitimate interaction, because if you think about what's actually going on is this cation plus will be at a very high energy. It may have a large kinetic energy or something like that, and when it's decaying it will be losing a lot of that energy and converting it into mass. And you can convert energy into mass, but you do have to have quite a lot of energy, as the equation E equals mc squared tells us. So all that's happening is the cation plus, which has a lot of energy, is turning some of that energy into more lots of particles. Okay, so if we begin drawing, you can see that this up quark will whiz straight across and become the up quark on the other side. Now we've got a strange quark. Well, it's an anti-strange quark. So you might be able to see that this anti-strange quark is going to interact with the anti-up at the bottom. The reason that is if you remember back to our standard model, it has to be a diagonal. If we're going to interact with quarks, it has to be diagonal or within the same generation. So this strange cannot interact with any of these anti-downs. It has to be interacting with this anti-up. So if we draw that in, we can have a little vertex there, and then we can draw our anti-up and then our anti-strange. I'll extend that line a little bit, and we can see that it's going to be the weak interaction. The reason that is because the quark is changing. You know it's not the gluon, and likewise with the electromagnetic force, the quark is changing. Okay, so it will be quite useful for this at this point to work out which W boson that is. And because an anti-strange has a charge of positive 1/3, because it's an antiparticle, it's switched around, so it's not a strange has a charge of negative 1/3, but an anti-strange has a charge of positive 1/3, and it's going to an anti-up, so an up has a charge of positive 2/3, and anti-up has a charge of negative 2/3. So you can see that we've got a drop in charge of -1. So because there's a drop over this vertex, we know that this must be a W plus to maintain that, so there's no charge created or destroyed. So now we've got a W plus boson here. We can see that there's going to be another interaction. So this is the point where you can see, okay, well, we can easily create a down and an anti-up here. An anti-down and an up from our W plus decaying. So that's what we're going to do. We're going to create a down and anti-up, and then you may see a slight problem. We've got an anti-down and a down here, that and there's nothing left. There's no interaction particle or anything like that. So what's actually going to happen here is something that is slightly different to what we've encountered before. This up, I'll get out the laser pointer, this up here is going to change colour between the second interaction point and being in this pion, and it's going to change colour, and that means it's going to emit a gluon. So if we have a look at what's going to happen there, is it's going to change colour and it's going to emit a gluon, and then that gluon can decay into an anti-down and a down. Now you may be wondering, well, how on earth is the energy from this created? And it's actually the up will have lowered itself in energy. but in fact you've got to remember that Feynman diagrams are not snooker balls, not representation of, you know, snooker balls smacking into each other. So we don't have an up rolling across here. In fact, what we have is a cat on. A slightly neater version is this. Okay. This is our final example of the more complicated ones, and what we have here is we have a sigma plus becoming a lambda plus and emitting a photon. Now I've put the quark compositions down below, so we've got an up, a down, and a strange, so we know these are baryons because there's 3. We've got an up, a down, and a strange here, and we've got an up, a down, and a strange here. So if we begin drawing the vertex, you'll see that with our composite particle we've got our curly bracket, and then we've got a sigma and a plus, we've got an up, a down, a strange, and then on the other side we draw a capital lambda and a plus, and then an up, a down, a strange, and we can see, on the exit we also have our gamma particle, and so we can see that the up whizzes across, so does the down, and so does the strange. Now where do we get the energy for this gamma particle? Where does that come from? Because you can see that everything just goes straight across. There's actually no interaction here so far. Now all that a sigma plus is just a high energy version of what we have on the other side. So all that happens is it just lowers itself in energy, and in doing so emits our gamma particle. So that's what we'd represent this as. So this is again slightly different to what we've seen before, because it's just lowering itself in energy. Thank you very much for listening.
I am Astronomy to GCSE, and this is an introduction to Feynman diagrams. This was a presentation I gave to my Physics Society about a year ago. I have slightly adapted it as I don't have a whiteboard, and I hope you're interested. This isn't part of the normal Astronomy to GCSE videos. It's not part of the syllabus.
Okay,
don't worry.
Brilliant.
It's just something extra I thought you might be interested in.